In this video, I'm going to introduce the concept of the derivative, and I'm going to do that through the concept of speed. Now, we all know what speed is, but there's two different types of speed that we're going to be working with. So the first is average speed, and average speed is just the distance you travel divided by the time it takes you to travel that distance. So let's say you got in your car and you went 30 miles in half an hour. So that means your average speed was 30 divided by half, or 60 miles per hour. But that doesn't mean that you're always going 60 miles per hour during your trip. For example, when you just started out, you had to study the car. Obviously, you were moving at 0 miles per hour, and then you sped up until maybe you got to 70 miles per hour, then you slowed back down when you're at your destination. So the average speed doesn't tell you about how the speed varies over your trip. But lots of times we don't want to know the average speed. We want to know, how fast am I going right now. And so, in your car, if you look at how fast you're going, that's what we call the instantaneous speed, not the average speed. The instantaneous speed is how fast are you moving at a specific instant in time, not over an interval. Another way we can say the instantaneous speed is it's the rate of change of the distance with respect to time. So the distance over time. So the problem, obviously, is how to calculate the instantaneous speed. Now, the average speed, we just took the distance and divided by time, but we can't do that because in instantaneous speed, we're looking at one instant, so time is equal to 0, and we can't divide by 0. So to find the instantaneous speed, what we're going to do is going to calculate the average speed over very short intervals. So let's say there's an object that's moving, and I want to know what the instantaneous speed of the object is after 3 seconds. And so to do this, we're going to begin by taking the average speed over some intervals around 3 seconds. So you can see here I have a chart of made-up data. So let's say we took the average speed from 3 to 4 seconds, 1 second after this 3 second. So the time interval is 1. And let's say the average speed, when we calculate it, is 100. And so next we take the average speed from 3 to 3.5 seconds. And it gets lower, 96.5. And then we keep taking the average speed for lower intervals. So we go 3 to 3.25, 3 to 3 and an eighth, 3 to 3 and a 16th, and so on. And as you can see, each time we take the average speed over a shorter interval, it gets closer and closer to 96. So it looks like, if we take the shorter we take the interval of the average speed, the more accurate an approximation it's going to be of the instantaneous speed. Because if we keep taking the average speed over a very short interval, say we took it from 3 to 3 and 1,000 seconds, then that's going to be almost exactly the same as the instantaneous speed at 3 seconds. So we can assume that if we keep taking shorter intervals, the average speeds will just get closer and closer to 96. So this leads us to believe that the instantaneous speed of the object at 3 seconds is 96. So we can say that the limit of the average speeds as we took shorter intervals closer to 3 approached 96. So the way we calculate instantaneous speed is not by taking distance over time, like with average speed, but it's the limit of the average speeds as we get closer and closer using shorter intervals. Now, obviously, we don't want to make a table every time we have to calculate the instantaneous speed, so let's look at how to do it with equations. So let's say we have some object, and we want to know the instantaneous speed at 4 seconds, or in other words, when t equals 4. And its motion is described by this formula s equals 16 t squared, where s is the distance traveled. So to find the distance traveled at any time, we just plug in t and find where s is. So the first thing we're going to do, since we want to find the instantaneous speed at 4 seconds, is we're going to find how further the object has traveled after 4 seconds. So we just plug in 4 equals t to this equation, and we find that it's traveled 256 at this time. So now we're going to find how long it's traveled at a time, a little after 4 seconds. So let's say h represents an interval of time starting at 4 seconds. So for example, if h is equal to 1, then 4 plus h, that just means at 5 seconds. So h is just a random interval of time after 4 seconds. And so during these h seconds, it's going to travel a distance k. So k represents the extra distance it travels past 256 when we extend the time interval by h seconds. So to find the distance traveled at 4 plus h seconds, we just plug 4 plus h into this formula. And so we get that 256 plus k is equal to this. So next what we're going to do is we're going to subtract this equation, S4, the distance traveled at 4 seconds is equal to 256. We're going to subtract this from this equation. And doing that leaves us with k, which remember is the distance traveled in h seconds. So average speed, is distance over time. So the average speed over h seconds is going to be k, the distance, divided by h. So we're going to divide both sides of this equation by h. And that gives us k over h, which is the average speed, is equal to 128 plus 16h. So now we have the average speed for some random time interval, h. But remember, what we did to find the instantaneous speed is take the average speed over smaller and smaller time intervals. So what we're going to do is take the limit as h approaches 0. Because h approaches 0 means that a time interval is approaching 0. So as h approaches 0, notice that the 16h term is also going to approach 0. So this is going to go away. So then we just have the limit as h approaches 0 of the average speed is equal to 128. So that means the instantaneous speed at 4 seconds is 128. So in this example, we used the letters k and h, but most of the time you're going to use the delta notation. So instead of h and k, you're going to use delta t and delta s. Now, if you don't, the delta just means a change in some quantity. So delta t really just means some time interval, which is what h is. And then delta s is the distance traveled in that time interval, delta t. So here we took the limit as h approaches 0 of k over h. So we can write that as the limit as delta t approaches 0 of delta s over delta t. And that is equal to 128, which is the instantaneous speed. And other ways we can write this, besides the limit of delta t approaches 0 of this, we can also write the s with a dot over it. You don't see this one much. And or ds over dt, s prime, this dash is called prime, or f prime of t. And so this is basically a derivative. A derivative is the limit of the average rate of change as the interval over which you're taking that average rate of change is approaching 0. So, as we've just seen, the derivative of the distance function gets you the instantaneous speed. And these are all notations for the derivative. So let's look at another example with just a regular function of y and x. So no more, distance and speed. So let's say we have the function y equals ax squared, where a is just any constant. So say we want to find the instantaneous rate of change at x is equal to x1. So we follow the same procedure. First we find out what does y equal when x is x1. And then we want to find if we plug in x1 plus delta x, where delta x is some makes it some x after this point x1, then the y will change by some value delta y. And so we plug x plus delta x into this equation and we expand this out. And then like before, we subtract this from this to find delta y. And then to find the average rate of change, we divide this by delta x. We have the average rate of change of y over this interval delta x. And so to find the derivative, we're now going to take the limit of this as delta x approaches 0. And so as delta x approaches 0, this term is going to cancel out, and we're just going to have 2a x1. So the derivative, or instantaneous rate of change of y with respect to x at the point x1 is 2a x1. And of course, we also have all these other notations. The limit of delta y over delta x as delta x approaches 0, y prime dy dx, f prime of x1. Notice we don't have the y with a dot over it. If you have a dot over it, that always means the derivative with respect to time, or t. We don't use that with other things. And so this process of finding the derivative, or the instantaneous rate of change, is called differentiation. So when you take the derivative of a function, it just gives you a new function, which is called the derivative, obviously. And that new function, the derivative, tells you the instantaneous rate of change of your original function at whatever value you want. So we started with the function y equals ax squared, and we differentiated to get the new function y prime equals 2ax. So the derivative tells you how fast y is changing with respect to x. And so we can also look at the geometry of this derivative thing. So let's review what we just did. So we had some curve, and we took a point x1, y1, and then we found another point x1 plus delta x, y1 plus delta y. So we have these 2 points, and where the points are separated by some interval delta x and delta y. So then we took the average rate of change, which is delta y over delta x. But what do we know? What else is this? We took the rise over the run of between these 2 points. So delta y over delta x is just the slope of the line between these 2 points. Okay, so the average rate of change between 2 points is really just the slope of the line between those points. But then we took the limit as delta x approaches 0. So if delta x approaches 0, that means this point is moving closer and closer to this original point. And the line between these points is getting closer and closer to what we call the tangent line. If you remember, a tangent line is just a line that touches the curve at exactly one point. So the line between these points as delta x approaches 0 is going to approach the tangent line. So another meaning of the derivative, not only is it the instantaneous rate of change of y with respect to x, but we can also think of it as the slope of the tangent line at a point x1. So looking at the derivative, we can instantly calculate the slope of the tangent line at any value of x just by plugging it into this function. So lastly, let's take a look at some other basic derivatives. So let's say the distance formula for an object is a constant, times t. So that means the object is traveling at a constant speed, b, because we know distance equals rate times time if the rate is constant. So if the speed is constant, then what do you think the instantaneous should be? The instantaneous speed should always just be the same, because the speed is never changing. So the instantaneous speed is the same as the average speed. So therefore, the derivative of this function if we think about it, it should be b. So the derivative of any function bx, where b is the constant, is just b. And then another case, if the object is not even moving at all, that means the distance function is just going to be a constant, because if it's not moving, the distance is not changing. So its instantaneous speed obviously should be 0 if it's not moving. So we conclude that the derivative of any constant function, y is equal to c, where c is a constant, the derivative should be equal to 0. And if we have a combination of these terms, so far we've looked at ax squared, bx, and a constant c. If we have any sum or difference of these terms, to find the derivative, we just have to take the derivative of the individual terms. So if we have this function ax squared plus bx plus c, the derivative, we look at each term by itself. This derivative is 2ax, this one is b, and this one is 0. So we just add up the individual derivatives to get the total derivative. So lastly, we're going to look at the concept of the second derivative. So, if we take the derivative of a function, then, why not? We can take the derivative of that derivative, and that's called the second derivative. So going back to distance and speed, if we take the derivative of distance, we get speed. If we take the derivative of speed, we get acceleration, because acceleration is the rate of change of speed with respect to time. So, how fast is the speed changing? And to denote the second derivative, we can, use an s with 2 dots over it if the derivative is with respect to time, or s with 2 dashes, s double prime, or f double prime at t.